One very nice thing about partition trees and partition theorem is that it easily generalizes to multi-level data structures. We have looked at the concept of multi-level data structures when it came to orthogonal problems, and you can do something very similar here. Essentially, you can take any canonical set and you can store it in a separate data structure to get a multi-level data structure. The main advantage of these multi-level structures is that they can solve much more complicated queries. Okay, so that's basically what I said. And in fact, similar to the orthogonal problems, you don't actually take the actual points that are over here. You can take other points that are related to them and store them in a data structure. I'll give an example so that it becomes clear how powerful is this idea. Imagine that I have this problem. I have a set of n line segments in the plane. I want to store in a data structure so that given any line, I could find a number or the list of segments intersecting the line L. Okay, so something like this. So given a query line, I want to find which ones intersect this line. This is in general, again, a very difficult problem, but we can solve it just using a multi-level partition tree. The way it works is as follows. Pick one endpoint of every segment, right? So let's say the left endpoint or right endpoint, doesn't matter. Pick one endpoint from every line segment. Now I have a set of points, okay? I can put them in a partition tree such that given any line, let's say any query line, do I have a picture here? Given any query line, I could represent the set of points, say in one half of the line, one half plane, using disjoint union of a square root n or roughly square root n canonical sets, okay? Then what happens here is that for every canonical set, let's say for this canonical set, I store the other endpoints of the line segment associated to them in a secondary partition tree. So now what happens is the following. You look at this half plane. You look at a canonical set that is fully contained in the half plane. So you look at a canonical set that is used to describe the disjoint union of this half of the plane. Okay, so let's say this triangle is one of them. You look at this canonical set, and now I have a data structure associated with the other endpoint. And now we make a very nice geometric observation. If one endpoint of the segment is over here, but the other endpoint is over there, then the segment should intersect. Then the segment must intersect the line. So therefore, to find the list or the number of the segment intersecting the line, I take the blue canonical set, I look at the structure that is built on these other endpoints, and I find which ones or how many of them are in the other side of the line. Okay? That's basically how it works. What is the space? Actually, I don't have the space analysis here. The space blows up by a log factor, more or less, right? Because you take your, let me go back to this picture here. This tree takes linear space. You take, for every canonical set, you store it in a separate data structure that takes linear space as well. So therefore, every point is stored in log secondary data structure. So this point is stored in its subtree as well as the canonical set of its parents all the way up to the root. Again, so the analysis is exactly the same to the canonical set situation that we had for the orthogonal problem. So the space blows up by a log factor. The interesting thing here is what happens to the query time. Okay, let me go forward again. What is the query time here? So here I have two different recursions. Right? So you have the recursion inside the top the top partition tree. Then you have the query time of the secondary structure. So basically the way it works is as follows. So let's say I'm looking at first this half plane. Okay, I know there are square root n triangles that are intersecting the boundary. Okay, for those triangles I do a recursion. So that is just a recursion on the triangles that intersect the boundary. But I could have R triangles up to R triangles, let's say in the worst case, all of my triangles in my partition could be inside the query. So it could be like this blue triangle here. If this happens, but then what I do is that I call the secondary data structure with the Q2 query time on them. So the query time is n over r. So the size of the subset that I'm calling on is n over r, and I have Q2, but I could have up to r of them. Okay, and then I also need to spend O of r time to inspect every triangle. Basically, the query algorithm is that you inspect every triangle. If it's outside, you ignore. If it's inside this half plane, you call the secondary data structure on them. If it's intersecting, you recurse. Okay, so that's essentially is the recursive formula for the query time. Now, what we can observe here is that we know what is this Q2, because Q2 is just a one-level data structure. The Q2 structure is no longer multi-level. So I know this solves to n over r to the square root n, essentially. And since r is a constant, essentially we could just absorb everything over here, and we could just rewrite this whole thing as roughly square root n, or n to the 1 over 2 plus epsilon. And again, in the exercise classes, we're going to show that this solves to this value. So essentially solves to some roughly square root n query time. But it allows us to do multi-level queries. And then you can just chain this idea as much as you want. You could have, so this was a 2-level data structure. You could have a 3-level, 4-level, 5-level, etc. data structure, as deep as you want to go. And in particular, you could solve more complicated problems, such as your input is a set of triangles. Your query is also another triangle, and you want to find all the triangles that contained inside your input. For that, you need a 3-level data structure.